So, very good evening, all participants and research scholar Himanshu Ranjan Das, who is going to read his thesis, who has submitted in April 21 for the award of PhD degree in Electronics and Communication Engineering, EC Department, New Shillong. This initiative we have taken to develop, you know, sorry, to develop scientific inquiry, to appreciate the outcome of research scholars, as well as dissemination of the information. PhD is a work which a research scholar uh, do in a span of 4 5 years. So it really needs very hard work, dedication, lot of sacrifice are involved behind these outcomes. So so I propose to Himanshu, please come forward and let us share, let us enjoy whatever you have documented. This a beautiful document is there, which has been submitted by Himanshu Ranjan. So I thought these texts are written. Who will read? Nobody as such is coming. It will be in the self of library or wherever. Only Himanshu or myself or somebody else who is coming to join this Lightwave Communication System Laboratory will read it. So I thought let us disperse this knowledge. Let us invite people and make part of this our beautiful journey which Himanshu Ranjan has traveled through. So he joined in 2015 in Department of ECE. He was the recipient of Rajiv Gandhi Fellowship, National Fellowship. That is one of prestigious fellows of even my both research scholars, Balvinder Kaur and Himanshu, both were so fortunate that they received this fellowship. And and as far as this today's session is concerned, please feel free anytime, any occasion you can interrupt. We shall be happy. In fact, this kind of environment we want to develop it. No hesitation. Please don't feel any hesitation wherever you feel that I have to learn this. I have to be clarified. Okay. So Himanshu Ranjan will try to give the answer wherever it is necessary to supplement by me. I will try to give the answers, as well as among the participants also whatever knowledge they have, they can also share. So this is a kind of total interactive and sharing based knowledge, interactive based knowledge, inquiry based information dissemination. Okay, it is not that one way transmission of information, and you will be only sitting passively. That kind of things we do not want, and we will encourage an active participation. Okay, so with this without wasting much time, let us invite Himanshu, over to you.
Yes, sir. Thank you, sir. So, first of all, a very good evening to all of you. So, now we shall start the thesis reading session. And the title of the thesis is Design of Directional Coupler Based Silicon Optical Modulator. So, I was under the supervision of Arya, sir. So, I have done or I have submitted my thesis from the Department of Electronics and Communication Engineering, School of Technology, Northeastern Hill University. So now, going to the abstract.
Yeah, I will show the piece. Yeah.
Yeah. So starting from the abstract, optical technology is poised to revolutionize the communication system. The leading candidate technology is silicon photonics, and the driving force of such a system is the optical modulator. The optical modulator is a device that modulates a beam of light propagating inside a waveguide. The beam of light may be carried over free space or propagated through an optical waveguide. Optical modulators have been improved dramatically in recent years, with a notable increase in bandwidth. However, the demand of optical modulators for high-speed communication are significant. and many questions remain unanswered as to whether silicon can meet the required performance metrics such as insertion loss, IL, extinction ratio, ER, the figure of merit, FOM, and energy consumption per bit. The presented work in this thesis discusses the plasmonic material based electroabsorption modulators. Two different plasmonic materials, indium tin oxide and vanadium dioxide, are used to design the modulators. A rigorous finite element method is used to optimize the device structural parameters. The investigated modulators showed enhanced performance in terms of IL, that is insertion loss, extension ratio ER, and figure of merit FOM, respectively. Also, a modified sidewall angled and a V-shaped ITO-based electro-absorption modulator was designed and investigated. The investigated modulators showed enhanced performance matrices compared to contemporary electro-absorption modulators in the literature.
Yeah. Thank you, Manshu. Actually, this is the entire abstract. So from here we come to know this this thesis belongs to optical technology, and optical technology has revolutionized this communication system, being a obvious advantage of tremendous bandwidth and very high speed data communication. So in that there is a device that is the active device that is called optical modulator. Optical modulator, it modulates the optical carrier frequency according to the instantaneous value of modulating signal. That modulating signal is in the electrical domain. However, this optical modulator will modulate the optical carrier signal, which is in very high frequency in terahertz, 193 terahertz range. But this fluctuation or this variation, any feature can be varied, suppose amplitude, frequency, or phase, as far as generalized terminology of optical modulator is concerned. Here, in this thesis, electro absorption modulator has been developed. In that, two two materials, two plasmonic materials, that is, one is ITO, indium tin oxide, that is the synthesized material, and another one is the vanadium dioxide, VO2. There are other materials also, but in thesis with the limited time and limited scope, these two materials have been used to develop separate modulators. This one modulator is based on the ITO, another modulator is based on the VO2 material, and we will look uh, what are their unique properties, why they are very much suitable for designing optical modulator. And here, optical modulators are assessed on various parameters. Those are insertion loss, extension ratio, and figure of merit. So these are the performance parameter. There are design parameter. We try to optimize those design parameter to maximize or to optimize output parameter, that is the insertion loss, extension ratio, and figure of merit. Beside that, one more that modulator, that is the V-shaped modulator, in which the side wall were modified with respect to existing modulator, and we proved there that its performance is better than whatever earlier was reported. Okay, so in abstract, any question, we shall happy to give the answer. Anyone, please? You can write in chat box also. We will take up. If no question, then Himanshu, we can move to chapter one.
So one question is there.
Yeah.
The
So
full form of
please read.
ITO is indium tin oxide.
Okay. Yeah. Okay, Vishal. Thank you for asking the question. Very good. So just among these are the list of abbreviation. Then this is the chapter one.
So we can show the content. What are the contents that we are going to read?
Okay, okay. That
Chapter
that
one.
that is also good. So let me go up. Please up. No, it is not coming. Content. You mean to content page?
Yes, sir.
And it is just tell me
So
where it
above,
is.
above, it's above, sir.
List of figure. Yeah, it is the content. So we can see here. Anyone is waiting? Yeah. So this is the chapter one. Please read it. Content of the chapter.
So, so this is the content. So in chapter one, so chapter one basically is the introduction.
Hmm.
So prior to this chapter, this certificate declaration, then plagiarism report, PhD coursework, award sheet, acknowledgement, abstract, list of tables, list of figures, list of abbreviation, and list of symbols are there, which support this thesis. So after that, coming to the main content are the chapters. So chapter one is the introduction, and this introduction chapter contains introduction section, then literature survey, then the motivation and objectives of the thesis, then the problem formulation, then scope of research, then what are the major contribution of this thesis, then what are the significant research outcomes, and at last how the thesis is organized. So now coming to this chapter two gives a dis-
Okay.
uh, details give details on electro-optic modulators. So how many, what are the different kinds of modulators? So how the what kind of losses are there in optical waveguides? Then how the performance matrices of the optical modulators are calculated, then the mathematical modeling of directional coupler based modulator is shown in chapter 2. After that, what are the applications of the optical modulators are shown, and then at last this summary of this chapter. Then coming to chapter 3 discuss in details the different architectural design of silicon based optical modulators. Here in chapter 3 we discuss the plasmonic materials, then what are different kinds of methodologies used to calculate the simulation parameters. Then there are two different kinds of modulators are reported in this chapter. That is the directional coupler based modulator, and one modulator that is a modified sidewall angle SI waveguide based electro absorption modulator. So we discussed the design parameters, the material characteristics, and the results which we have got as an output from the simulation of these devices are discussed in this chapter 3. And at last, in section 3.6, the summary of this chapter is discussed. And in chapter 4, the title of the chapter 4 is Comparative Analysis of VO2 and ITO based electro absorption modulator. So here basically two different types of modulators are discussed, that is vanadium dioxide based and ITO based, that is indium tin oxide based. So here we calculate the parameters of both the modulators based on different plasmonic material, and then we compare the result of the proposed vanadium dioxide based and ITO based electro absorption modulator with the existing modulators in the literature. And chapter 5, coming to chapter 5, the title of chapter 5 is a V-shaped ITO based electro-absorption modulator. So here we have designed a V-shaped indium tin oxide based electro-absorption modulator, and we discuss its performance matrices, and we analyze the structure in this chapter. And now coming to chapter 6 is the conclusions and the future work, and it includes the limitation of our present work and future works. And at last the bibliography, and then list of publications and reprint of the first page of journal article and the curriculum vitae.
Yeah, we can move to now chapter one. So total chapter are six. Out of these, chapter 3, chapter 4, and chapter 5. Three chapters are contributory chapters. and other chapters are supporting. So out of these three chapters, three SCI index publication have been done. So that is why it becomes contributory chapter. So any question now? No. Okay. So this is the
So
chapter one.
now,
Yeah.
yes, sir, I shall start from introduction. That is section 1.1 introduction. Optics is an old and respected field, including the generation, propagation, manipulation, modulation, and detection of light. Along these lines, photonic is the science and innovation of light with an accentuation on applications. At the core of photonics are advancement for creating, communicating, intensifying, balancing, and recognizing light, and especially utilizing light for useful purposes. It resembles vigorously on optical innovations. However, it mirrors the developing tie among optics and hardware manufactured by the expanding job that semiconductors, materials, and gadgets play in optical frameworks. For all, photonics is considered one of the vital advancements of the 21st century. It supplements gadgets as optoelectronics and displays a substantial market development which is required to proceed for years to come. Regular photonic application reasons are data and correspondence innovations, medical services and life sciences, optical metrology, detecting and biosensing, safeguard and space innovation. The market research and strategy consulting companies announced the overall silicon photonic market is reaching 3.9 billion US dollar in 2025. The silicon photonic market forecast for 2019 to 2025 is shown in figure 1.1. The market of data transceivers is expected to increase from $364 million to $3.6 billion by 2025. Overall, the market is expected to increase from $480 million in 2019 to $3.9 billion in 2025. The focus of this thesis is on plasmonic material-based silicon optical modulators. Optical modulators in long-distance optical fiber communication became critical and widespread shortly following the demonstration of reliable, compact, low-loss, and high-speed optical modulators. Yet, optical modulators are fundamental to optical communication and have a long history. Optical modulator technology has also progressed significantly during the last 2 decades, as described and illustrated in the forthcoming chapters.
Yeah. Before moving to 1.2, can you little bit give this explanation of figure 1.1?
So, the figure 1.1 shows the silicon photonic market forecast by application. Means by application, what is the market? That is a cost market in the industries. So here, if we see in 2019, the overall silicon photonic market is $480 million. That is US 480 million US dollar, out of which $364 million is acquired by data transceivers, and 170 market is captured by long haul transceivers. So coming to 2025, the same market is expected to increase to $3.6 billion, and the long haul transceiver market is expected to increase up to $186 million. So here we can see how much potential or how much demand is there of silicon photonic in the industry.
Okay.
So here
Besides
data
that,
center.
yeah, beside that, there are other areas where the silicon photonics is changing the technology or advancing the technology beside
Yes,
whatever data center and long haul. So
long.
this Himanshu's work is basically in data center long haul communication only. So the way market is growing, whatever work Himanshu has done, it has tremendous demand, tremendous relevancy. Okay, so now yes, any question till now you can ask anyone. So any background information do you feel participants should be given? Are you following the way we expect? We are talking about basically optical communication field. In that optical communication, we have trans receiver, then channel, sorry, transmitter, channel, and receiver section. So in transmitter side, we have modulator, basically central section. The transmitter side is one of the modulator. Modulator is required for long haul transmission for high speed data communication and to gain very high bandwidth. For today's communication, we need very large bandwidth. Even this whatever online communication is being conducted now, this it requires large bandwidth. So, in order to support this advanced technological requirement, we need very high bandwidth system. So, optical domain is the domain which provides such kind of facilities. So that is why there is a need to work in the optical domain, and in the optical domain, the optical transmitter, more specifically, our data center, where huge data is saved. So there also we need transmission, means within the data center for short distance communication we need high bandwidth, high data, high computational efficiency. There also we need optical modulator. So in this line, one innovative modulators is being modeled and designed, and its work has been published. So this is the, I think, requisite background which if you are missing. So anything more if you wish to know, please let me know. And thank you for patiently listening. It will be nice if you can post the question also. Thank you, Vishal, if it is clear to you. So can we move to literature survey portion? Okay, Himanshu, over to you.
Okay, sir. So now coming to section 1.2, literature survey. So literature survey is an essential part of a thesis. So from here we will come to know whatever literature was there previously, and from based on that, what we are going to do. So whatever literature I have read has been pointed out in the literature survey. So I will go through it. So starting G.T. Reed and G. Mashanovich, F.Y. Gardis, and D.J. Thompson. They have characterized a silicon optical modulator based on its parameters like doping concentration, wavelength, and switching rate. So this reference is reference number 3. And after that, L. Ahmadi, M. Hiltuni, P. Stenberg, J. Hiltunen, S. Aikio, M. Rossi, J. Sarinen, and S. Hokanan demonstrate a polymer slot waveguide young interferometer coated with a bilayer of aluminum trioxide and titanium dioxide. This approach enables relaxed dimension of the polymer waveguide, which simplifies the structure's fabrication with a resolution of 50 nanometer. The layers were coated by an atomic layer deposition (ALD) technique. The device's feasibility was investigated by exploiting the interferometric structure as a bulk refractive index sensor operating at 975 wavelength for detection of an ethanol water solution. A refractive index of 1 into 10 to the power minus 6 refractive index unit with a sensing length of only 800 micrometer was detected. This has been quoted in reference 4. After that, S.C. Hoseininajad and N. Komjani presented a comparative study of hybrid and non-hybrid plasmonic slab waveguides based on 1. and two isolated graphene layer hybrid graphene metal structure. The analyses were performed by an analytical approach based on transfer matrix theory and numerical approach based on the finite element method. Propagation properties of the structures were exploited at terahertz frequencies. Four characteristic parameters compared the waveguides. That is complex refractive index, propagation length, spatial length, and field distribution according to the layer thicknesses and graphene Fermi level. That is a chemical potential. In reference 5. After that, J.T. Kim demonstrated that by electrically tuning the material's refractive index, the directional couplers coupling efficiency is switchable, and hence the modulated signal is obtained. An extinction ratio of 6.7 dB and 2.3 dB at 1.31 micrometer and 1.55 micrometer wavelength is achieved, and this is denoted by reference 6. DC Geographopoulos et al. Has modeled a hybrid electro-optic plasmonic modulator based on directional coupler switches. The modulator shows an extensive operating window with low crosstalk values and minimal footprint concerning similar coupler switches of the silicon photonic platform. This has been denoted in reference 7. Also, AP Vasudev, J.H. Kang et al. Theoretically demonstrated a highly effective optical electro-absorptive modulation in a silicon waveguide overcoated with indium tin oxide. The modulator leverages the combination of a local electric field enhancement and increased absorption in the ITO when this material is locally brought into an epsilon near zero, that is ENZ state, via electrical gating, thus leading to large changes in model absorption upon gating. They found that a 3 dB modulation depth can be achieved in a non-resonant structure with a length under 30 micrometer for the fundamental waveguide modes of either linear polarization with absorption contrast value as high as 37. They also showed a potential for 100 femtojoule per bit modulation with a performance sacrifice. So this is denoted in reference 8. Now, Shi Lin and A.S. Helmy demonstrated a dynamically reconfigurable nanoscale modulator utilizing coupled hybrid plasmonics. In their work, they reported a nanoscale modulator architecture that elevates this trade-off while providing dynamic reconfigurability that was previously unattainable. This was achieved with the aid of three mechanisms. Number one, utilization of ENZ effect, which maximizes the attainable attenuation that an ultra-thin active material can inflict on an optical mode. Number two, the non-resonant coupled plasmonic structure, which supports modes with a long-range thermal propagation. Number three, triode-like biasing scheme for flexible manipulation of field symmetry and subsequently waveguide attributes. By electrically inducing indium tin oxide to be in a local ENZ state, they showed that a Si slash ITO slash HFO2 slash AL slash HFO2 slash ITO slash Si coupled plasmonic waveguide could provide amplitude modulation with extinction ratio equal to 4.83 dB per micrometer, insertion loss equal to 0.03 dB per micrometer, and energy consumption equal to 14.8 femtojoule, showing at least an order of magnitude improvement in modulator figure of merit and power efficiency compared to other waveguide platforms. Reference number 9. M. Ataya et al. Proposed a novel ultra-compact electro-absorption optical modulator based on a silicon reef waveguide and numerically demonstrated its performance. The proposed design employs two types of transparent conductive oxide TCO layer with different carrier densities to achieve high modulation efficiency and low optical insertion loss. The thin TCO layer with high carrier density enables efficient modulation through the metal oxide semiconductor structure. Using the ITO bilayer with optimized carrier densities, they numerically demonstrated a 4.3 dB extension ratio and a 2.6 dB optical insertion loss with 1 micrometer device length. They estimate that the modulator operates under a low driving voltage of 1.3 volt, exhibiting an ultra low energy consumption of 22.5 femtojoule per bit. Reference number 10. M.K. Shah et al. Have investigated the enhanced performance of ITO-assisted broadband electro-absorption optical modulator. The modulator architecture comprises of silicon slash hafnium dioxide slash indium tin oxide slash silicon stacked upon a silica substrate. The balance between extension ratio insertion loss was maintained by engineered waveguide structure and choosing the modulators on state at lower carrier concentration regime. The influence of sidewall angle silicon waveguide on mode power attenuation change and consequently modulator footprint and energy consumption were analyzed. The calculations showed that the electroabsorption modulator can be realized with extension ratio equals to 6.81 dB per micrometer, insertion loss equals to 0.019 dB per micrometer, figure of merit equals to 337, energy consumption per bit equals to 20 femtojoule per bit. Also, comparison over its similar kind shows improvement in extension ratio, insertion loss, figure of merit, device footprint, and energy consumption. All in all, the proposed modulator featured a simple structure, smaller footprint, and well integrated compatibility. Vanadium dioxide (VO2) is a phase change material, that is PCM, that exhibits a large change in the complex refractive index based on unity upon switching from its dielectric to its metallic phase. Although this property is key for designing ultra-compact optical modulators for only a few microns in footprint, the high absorption of vanadium dioxide leads to appreciable insertion loss that limits the modulator performance. In the work of H.M.K. Wong and A.S. Helmy, reference number 12, through theory and numerical modeling, they reported a new paradigm which demonstrates how the use of a hybrid plasmonic waveguide to construct a vanadium dioxide based modulator can improve the performance by minimizing its insertion loss while achieving high extension ratio in comparison to a purely dielectric waveguide. The hybrid plasmonic waveguide containing an additional metal layer with even higher loss than vanadium dioxide enables unique approaches to engineer the electric field intensity distribution within the modulator's cross section. The resulting figure of merit equals to extension ratio slash insertion loss observed was higher by simply incorporating vanadium dioxide into a silicon wire waveguide. A practical modulator design using this new approach, which also includes input and output coupler, yields extinction ratio equals to 3.8 dB per micrometer and insertion loss equals to 1.4 dB per micrometer, where FOM equals to 2.7 with a 3 dB optical bandwidth greater than 500 nanometer in a device length equals to 2 micrometer and cross-sectional dimension equals to 200 nanometer into 450 nanometer. Also, a Josh, Joshaghani et al. Have demonstrated hybrid plasmonic switches that use a transition metal oxide, that is
Himanshu,
vanadium
give a
dioxide.
pause.
Yes, sir.
Give a pause here. Okay. Actually, dear participants, we know there is a literature survey section in every thesis, or where we are going to pursue any research high level, means yeah, dissertation work. Literature survey is one of the important. What is the purpose, why we need basically literature survey? Actually, literature survey in a particular field on a given topic is a search of what is the state of work, what kind of work is going on, what are the results available in the literature, what are the challenges, because this literature survey also tells that what are the limitation of their work, and further what can be done in future. If you read the paper, large number of paper in your discipline or your area, you will come to know not only the results, reported result, but its limitation. After knowing those limitation, you can work over on that. That will open a window for working ahead. Okay, so within a given time with limitation, one has a one has a limitation to do the work. Okay, but rest work which has not been done, that also is there in the reported result, which we used to study via literature survey. So that is the purpose, and so that we can build up our research based on whatever already has been done. We should not do same thing again and again out of ignorance. So that is why contemporary literature survey is very very important, one thing. And while doing literature survey, see, this internet is ocean of knowledge. We should not lose, we have to be very very focused. So there, while reading any article, we have to read first title, whether title consist of keywords where you are interested. This is what, once it is decided, yes, it is pertaining to your area, then we have to read the abstract. Abstract gives the basic idea of what are the content inside that. So there, it after reading that abstract, 90% job is done, means whether you are going to read the paper or just simply pass on other one. So this is where this is a part of extensive literature. Once we have decided that yes, this paper is worth to read, because it is in my area of research or my area of interest. While reading, we have to first go through the published results, means in form of diagrams, figures, tables. There you will find what are the new things. Then come to the result section, description, result and discussion. And after that, you can go through the introduction part, then methodology. This is how we do literature survey. However, uh, while writing, it is another way. Okay, so this is the tips which I wanted to give here. And extensive literature survey, critical literature surveys, very very essential. We have to look critically what are the methodology have been used to get the result, whether it is convincing, logical or not. One thing. Second thing, uh, these results, whether uh, retrievable, or if I redo it, resimulate it, I should get the same result. It should not be that A has done. If B is trying to do the same thing, B is not able to do after following all steps, whatever it is described in the paper or whatever. It should not be like that. It should be consistent. Repeatability should be there. So so these are the tips. And you see, through this literature survey, few keywords are there. We after see while doing literature survey, we have to read lot of papers. Then we have to filter out. We have to filter out based on our focused area. So this needs lot of hard work. Where unless you put really some time, some dedication, then only you will have lot of idea. Otherwise, initially, people find it's very very difficult to understand even basic terminologies. It is really very hard to understand, but slowly you read it again, try to get the meaning, and then in a ascending order form, try to write those things as a literature survey. Okay, and be very specific, concentrated. First thing, what is the result, how result was obtained, that is called methodology. third one is what is its significance, whether it is really progressing, developing, it has some significant impact, or just merely it is a reporting. These things you have to take decision. And fourth one, how convincing is that? See, nowadays in your internet, every kind of results are available. So please refer very standard journal, not any anything which is very much very easily available to you. It should not be that criteria. Go for IEEE paper, Springer paper. Okay, so whenever this you can contact your supervisor, they shall able to give you best uh, referencing sites or journal name. Okay, so any question, participants? No, then we can move ahead. Over to you, Himanshu.
Okay, sir. Also, Joshua Ghani et al. Have demonstrated hybrid plasmonic switches that use a transition metal oxide, that is vanadium dioxide. The result showed that the electrically controlled plasmonic switches could have performance characteristic competitive and superior to their dielectric counterparts through the choice of material and design. This work opens the path towards using vanadium dioxide for subwavelength size scale yet efficient optoelectronic devices. The vanadium dioxide phase transitions ability to initiate a sub-picosecond timescale by electric field is promising for ultra high speed and low power modulation, and insertion loss equals to 0.86 micrometer, extinction ratio 2.3 micrometer, and FOM 2.67 was calculated for the device respectively. Reference number 13. A similar kind of plasmonic modulator slash switch was designed and demonstrated by D. Chauhan et al. They had designed a plasmonic modulator based on vanadium dioxide material and observed a modulation depth of 19.44 dB, loss of minus 2.55 dB, and FOM of 7.62. Reference number 14. M.Y. Abdelati et al. Designed and demonstrated a silicon optical modulator based on tri-coupled waveguides, where ITO was used as the plasmonic material. The device was optimized by finite difference time domain (FDTD) electromagnetic simulations for the modulator length of 21 micrometer and ER of 6.14 dB at a loss of 0.06 dB was observed. Also, when the modulator length is increased to 34 micrometer and ER of 11.43 dB at a loss of 1.65 dB was observed at 1550 nanometer application wavelength. Reference number 15. MM Badr et al. Designed an ultra-fast silicon electro-optic modulator based on ITO integrated directional coupler. They have explored the ENZ characteristic of ITO material and incorporated them into the device structure. They have introduced an ITO/HFO2 combination in the coupler section to manipulate the propagation of light. They have observed an extinction ratio of 9 dB, an insertion loss of less than 0.9 dB, and energy consumption per bit of 4.35 femtojoule per bit, respectively, at the communication wavelength of 1550 nanometer. Reference number 16. R. Amin et al. Demonstrated an heterogeneously integrated plasmonic material-based Mach-Zehnder interferometric modulator on silicon on insulator SOI platform. The device enables spectrally broadband operation across the entire telecommunication infrared C-band. Such kind of device opens up new possibilities of high density photonic circuitry. Reference number 17.
Yeah. So give a pause here. So through this literature, certain terminologies are there. These terminologies are like as far as material is concerned. So plasmonic materials, that is VO2, ITO, and some other dielectric materials have been used. And as far as performance parameters are concerned, so we can have these parameters on tips like on our finger tips, that is the extinction ratio, figure of merit, and insertion loss. So these are the performance parameter, and keeping it to those things into mind, Himanshu has sorted out most important articles. Although he has read lot of articles, but out of that most important articles, that is about say 17, has been sorted out and then put in the ascending order so that it can be beautifully expressed here. Okay, so any question before going to motivation and objectives of the thesis? Why in fact researcher has started the working, what motivates him 5 years 6 years back in 2015, and then after doing literature survey, how objectives were set, not how but what are the objectives set, how. So after doing literature survey and in consultation with me only, he set the objectives, because without setting the objective it is very difficult to travel your research journey. So we have to be very focused. And objective, there are three characteristics while setting the objectives. Those characteristics are: objective must be very very specific. Objective must be very very specific. It should not be generalized. It should be very very specific. Second characteristic is that it should be measurable. Measurable means you can quantify and one can verify it. Okay, suppose an objective is set, and if I'm not able to measure whether you are able to achieve or not, so that objective doesn't qualify to be as objective. So it should be measurable. So first one is the specific, second one is the measurable, and third one is the achievable. You should decide your objective that is achievable within the given circumstances, with your ability, with your resources, within your time, because your degree program is a time bound. It cannot be so long. So suppose you are doing say BTech, so 1 year maximum or 6 months, sometimes as a dissertation work. You are doing say MTech program, dissertation program, so maximum 1 year is there. Within 1 year, I think 8 to 9 or 10 months you will get for doing research work, and then for PhD 4 to 5 year. So that is why select your objective very carefully, and it should be specific, measurable, achievable. These three keywords please remember: specific, measurable, and achievable. You should able to achieve it. Okay, yeah, some risk will be there that we have to take, but these risks should be calculated way. Take a calculated risk, then go ahead. Okay, so now Himanshu, can we go to motivation and objectives? Before going to, if anyone has query, please let us know. And thank you for being here. 17 are here, 17 participants. So over to you, Himanshu. Come on, does
Okay, sir.
motivation? What motivates to carry forward this research work? And after that, what objectives you have set? Please go ahead. 1.3 section.
Yes, coming to 1.3 section, motivation and objective. The optical modulator plays a vital role in the field of optical communication. It is a thrust area and burning issue where research and development needs to be done, as the market for high-speed communication is proliferating wildly at present of COVID-19 pandemic situation, where all the academic activities, businesses and communications are held through online platforms like Google Meet, Zoom, Skype, etc., which demand high data rates. This research work will be a platform that enhanced and develop the area of optical communication. So
Yeah,
here figure 1.
yeah. Can you explain this figure also? Yeah, it is there. Hmm.
Yeah, so we can see in figure 1.2, it shows the operating speed versus critical dimension. So here we can see that in past, the size of the devices were larger as compared to present. In past, the size of the devices were 1 micrometer, 10 micrometer, 100 micrometer. So this micrometer is small only, but compared to today's devices, this footprint were very large. So what we can see from figure 1.2 is that if we go to electronic component, then we can decrease the size of the devices. If we use electronic component in circuit, we can decrease the size. But however, there is a limitation. With decrease in size of electronic parts, the operating speed is limited. Means we can't go beyond megahertz range if we use only electronic components. Similarly, if we use photonic components, we can go for higher operating speeds, that is up to terahertz range. But using photonic component, there is a trade-off. The trade-off is that the size is limited. We can't decrease the size below 100 nanometer. So we go for plasmonic. So plasmonics, utilizing or using plasmonics, we can deal with these problems. So using plasmonics, we can make the device smaller, as well as we can achieve higher operating speeds. So this figure 1.2 is showing this only. Why we go for plasmonics. So figure 1.2, here it shows the operating speed as a function of the device dimensions. Reference number 18. As the demand of maximum number of devices on a single chip increases, the package density of PIC, that is photonic integrated circuits, increases. The devices are being fabricated on a nanoscale. However, the decrease in device dimensions affect the electronic and photonic components. The RC delay hinders this signal speed due to the wire resistance and capacitance, resulting in low operating speed. Similarly, the problem in photonics is the diffraction limit in size. Plasmonic based devices are used to achieve high operating speed at a low device footprint to overcome such problems. Also, plasmonics naturally interfaces with smaller size electronic components. Also, various silicon optical modulators have been designed to date with the aid of innovative design schemes, including a Mach-Zehnder interferometer, MZI, a microdisc, and a microring resonator structure. The silicon optical modulators uses the relative phase shift of two propagating waves, which are based on the electrically tunable refractive index of SI. These modulation mechanisms are effective. However, the MZI-based modulators have suffered from a large device footprint because of silicon's weak electro-optic effect. The micro-ring-based modulators are limited due to their very narrow spectral bandwidth. Therefore, an optical modulator based on plasmonic material is highly desirable for compact and broadband communication. Now, coming to the objectives of the thesis, the objectives of the thesis are as follows. Number one, to develop a mathematical model for directional coupler based silicon optical modulator. Number two, to design the architecture of the optical modulator based on 2-core, 3-core hybrid plasmonic directional coupler. Number three, to optimize different parameters like extinction ratio, doping concentration, coupling length of the waveguide, and refractive index of the material used. Now, the last objective is to evaluate the performance of the directional coupler based silicon optical modulator.
Yeah. Give a pause here, Himanshu. So this motivation, this diagram one or figure one says, enough motivation that we have to increase the package density, and package density means number of transistors or devices in a very very small area. So that is the demand. Miniaturization is essence, is throughout the years we are trying to minimize the area. On the other hand, we should not compromise on operating speed. So this is in past story, and now this is electronics. With the help of electronics devices, we can miniaturize. In fact, 7 nanometer channel width CMOS technology is there. But again, the constant is that, as Himanshu told, that operating speed. is not very high. There is a limitation in the electronics. However, if we just shift from the electronic domain to photonic domain, you will see even past photonic domain is giving gigahertz to terahertz range, operating range. Yes, earlier a little bit bulky devices. However, the limitations of reducing the size as well as maintaining the high speed is maintained by or can be achieved. This gives hope, can be achieved by using plasmonic materials while designing optical devices, circuits, and systems. So these plasmonic material based devices are unique materials. These are synthesized and you know invented materials by the researchers. Okay, so that is the main motivation why we are why we are using this plasmonic material. In the electronic domain, of course, Mach-Zehnder interferometer and ring resonator based modulators are there. In this also, people are trying to minimize using silicon based optical modulator, that is called plasma dispersion based modulator, where p-n junction is used. And ring resonator, it has very high speed but only suffers with the lesser bandwidth. It has higher bandwidth, but it suffers relatively larger footprint if we compare with this MRR and MZI. However, these two still has larger size compared to plasmonic material based modulator. So this is the very motivating, and this is the thrust area. Here lot of work can be done. People have not so much worked on that. Okay, so this was the motivation to take up this research work, and that too uh, in 2015. So even 2015 it was a very hot topic. Still people are working on that area. So with after identifying the area, then we narrowed down, we enumerated basically objectives, that is the four objectives. First started from the mathematical model. We have to mimic the functions, the operations in mathematical language, so that we can simulate, we can get its theoretical results, how it behaves. So it starts from solving the Maxwell equation, because here light wave these wave nature of light is being exploited. Mathematical modeling should be done, particularly for this directional coupler based. And then it's different architecture has to be explored to optimize the output parameters. And then what are the different parameters which can be optimized, that output parameters? So maybe the extension ratio, doping concentration, coupling length, etc. And then after that, evaluation. Okay, so any question before going to problem formulation? In chat box also, you can write, participants. Keep looking, and I have sent this form also for the registration purpose, so that I should have list of those participants. Later on, I can give certificates also after completion of this uh, thesis reading. This is really a little bit long journey, but we shall able to complete it with good good outcomes. Yeah. So Manshu, over to you. Let us move on now. How to
Okay.
formulate the problems? Statement of the problem should be well formulated. So over to you, Himanshu.
Okay, coming to section 1.4, there is a problem formulation. The above discussion shows that the demand for a high data rate is proliferating and the size of the electronic optic components is being reduced to the nanoscale to increase the overall package density to meet the requirements of low device footprint, high speed communication. Therefore, we have formulated the following design and analysis problem for our research work. Point number one, designed a miniature electro absorption modulator EAM for PICs with modified sidewall angled silicon waveguide for enhanced performance matrices. Point number two, propose a EM electro absorption modulator based on two different plasmonic materials, namely VO2 and ITO, and optimize their structural parameters. Point number three, Material characterization and structural analysis of a V-shaped hybrid plasmonic EM based on ITO.
So these are the problem formulation. How means designing a miniaturized electro absorption modulator. Electro absorption modulator means a modulator which absorbs the light at certain condition. In another condition it should simply pass on. So if it will simply pass on means say on condition, and if completely absorbing the light means off condition. So this is the basically meaning of electro absorption, means through electronically, by giving some biasing current or voltage to the device, we are changing the its waveguide properties. Means whenever light is going, it will light will be absorbed in the device, or simply it will pass. But that two phenomena, on and off, is controlled by electronics. So that is why electro absorption. And modulator means because we are varying one of the parameter of light, and that is called modulator. Different parameter, but here still uh, as far as modulator is concerned, we are at primitive stage compared to electronic domain modulator. Because in electronic domain you can modulate amplitude, you can modulate frequency, you can modulate phase, you can modulate polarization, etc. Of course in that also there, but not in an integrated electronic form, or particularly for uh, this plasmonic material based. Since it is somebody was there. So the what I was telling you, give biasing so that on and off can be done, but this on and off should be according to the modulating signal as per the information signal, and that is what is simple meaning of modulator. As an electronics engineer, we are aware about this modulation, but this modulation is now in the electronic domain. See, optical signal has very high bandwidth, and switching off this very high bandwidth is very difficult. On and off, on and off, this is this required special technique. It is not so easy the way we achieve it electronic domain. Electronic domain frequency is less and very specific, means at particular one frequency you can generate the signal, but in optical it is not possible. Somewhere it has width. Even we assume that this is 1550 nanometer, but source, that is the laser, is not able to generate single frequency. It has some width. Okay, so that makes your problem basic. That is why on and off becomes very difficult task. Okay, so can we move next? How many pages are there still, uh, Manju?
So 3 pages.
Only three now. Okay, yeah.
Yes, sir.
Okay, so we can complete today's task. That is the chapter one. So with this now, what is the scope of research? Once we have formulated the things, so we have to scope this with how much we can see, how much we can look upon, or how much we can catch it up. Okay, so everything cannot be accommodated in a research work, particularly which is pursuing by research scholars, PhD scholars. So that is why we have to narrow down the scope, but that scope has to be determined. That scope has to be written. Okay, so that we should know, and examiner or any evaluator should not ask or expect out of scope questions. So if from our side we have written that scope, that is a very good idea. Yes, uh, Himanshu, over to you.
Okay. Coming to section 1.5, the scope of research. This dissertation explores the possibilities of designing an electro-absorption modulator based on plasmonic material. Two different plasmonic materials, namely indium oxide and vanadium dioxide, have been used to design the electro-absorption modulators. The optical characteristics of ITO and VO2 have been discussed in this thesis. Different architectural design for the electro-absorption modulators like the directional coupler, modified sidewall angle, and V-shaped ITO has been investigated and discussed in this thesis. Also, a comparative analysis of vanadium dioxide and indium tin oxide based modulators have been discussed. These devices are compatible with CMOS technology and suitable for photonic integrated circuits. Furthermore, other plasmonic materials like graphene, gallium, zinc oxide, etc., can be also used to design an electro-absorption modulators. However, we have focused our work on ITO and VO2 based modulators.
So now you can see here there are other types of plasmonic material, that is graphene, gallium, doped zinc oxide, and some more are there in the literature. But we have not worked on all those because of our limitation. Okay. However, we have extensively used this ITO and VO2. So this is what I was trying to tell. One can ask why you have not used. Where is the result of graphene? No, because this is not in our scope. Okay. So any question before moving to major contribution? Please interact. That shall be good. You can write in chat box also. I will take up the question. Okay, if no, so come on this major contribution means what are the outcome, because chapter 1 is very very important. In fact, it gives the gist of entire thesis. So let us see what are the outcomes, major contribution of the thesis. Over to you, Himanshu.
Okay, coming to section 1.3 or 1.6, major contributions of the thesis. This dissertation presents the design and performance analysis of silicon optical modulators. It explores the possibilities and advantages of enhancing the device's performance matrices in terms of IL, ER, FOM, and energy consumption per bit by optimizing the device's structural parameters and utilizing the characteristic properties of the plasmonic materials. The essential and critical contribution of the thesis is as follows. Point number one, design a directional coupler based silicon optical modulator for high speed optical communication systems at 1550 nanometer application wavelength. Point number two, an indium tin oxide ITO plasmonic material based electro-absorption modulator's performance has been improved in terms of energy consumption per bit from 20 femtojoule per bit to 6.8 femtojoule per bit, FOM from 337 to 422, insertion loss from 0.019 dB per micrometer to 0.016 dB per micrometer by modifying sidewall angle silicon waveguide structure at 1550 nanometer application wavelength. The epsilon near zero ANZ and the waveguides model analysis were done for electrical characteristics and single mode light propagation, respectively, in the ITO assisted EM modulator. Now, coming to point number three, design and analysis of two CMOS compatible plasmonic EMs based on VO2 and ITO. The performance matrices have been improved in terms of IL, ER, and FOM. Rigorous finite element method FEM has been used to optimize output parameters based on the input device parameters. The IL, ER, and FOM for both the modulators were 0.651 dB per micrometer, 5.85 dB per micrometer, 8.98 respectively for VO2 based EM, and 0.025 dB per micrometer, 3.07 dB per micrometer, 122 respectively for ITO based EM. Coming to point number four, performance analysis of a V-shaped ITO based highly efficient EAM has been designed and simulated with 220 nanometer and 350 nanometer waveguide height to meet the explosive demand of miniature photonic integrated circuits, high-speed optical communication systems. COMSOL multiphysics-based rigorous finite element method was used for optimizing the geometrical structure of the EAMs, that is V-shaped and various dimension for 5050 nanometer operating wavelength supporting single mode transverse magnetic polarized light. Also, the result of the investigated devices were compared with contemporary devices in the literature.
Okay, so these are the contribution basically. So first contribution is here, directional based optical modulator. This is first. Second one, this where side wall, we have modified this side wall angle to optimize, and we can see here the existing was say 20 femtojoule per bit to 6.8. So energy consumption has been minimized if we modify this structure. So here basically structure was optimized, keeping all other parameters same. So it was a judicial decision to optimize the structural parameter, and this one article was published in Optic. Oh, what is this? Sorry. Optic. Okay, it's what is this impact factor? 2 point.
2.26, I think.
Okay, and next was this two CMOS compatible plasmonic material based EOM. So what are the two plasmonic material? That is VO2 and ITO. And not only design but performance, its performance matrices have been compared, so to identify which modulator suits for which application. That has also been done. And what are the method? So we use their finite element method, which is available in COMSOL multiphysics, to do all analysis. And one article was published out of this in Optic Communication. Optic Communication. And it has also how much, do you know, Himanshu?
Around 2.4.
2.4. And this is
Yeah.
Q1 type journal, and this is Q2 type. And then third one, this V-shaped ITO based. So again here, see what we are trying to do. We are trying to characterize the material in the best way. Second one is the structural changes. Okay, so change in the structure and use suitable material to achieve figure of merit at higher level. Okay, and one important thing is that most of the devices which we use in uh, optical domain, particularly ring resonator based and Manzanite interferometer, they are very much suitable for TE mode. But this plasmonic material is very much suitable for TM mode. So it is a kind of supplementing also. We can use both. So polarization division multiplex technique also can be used to further exploit the available bandwidth. Okay, or spectral efficiency can be improved by using both modulators on the same chip. So with this, any question before coming to the significance of research outcomes? No. Let us do first. How many pages still? Okay, this
Still
much.
2 page, 1.5 pages left.
Okay, yeah. I think people have patience. Okay, thank you, participants. Yes, go ahead.
Now, significance of the research outcomes. The significance of the research outcomes are as follows. A modified sidewall angle based silicon electro absorption modulator is designed. The device shows enhanced performance matrices and is compatible with existing CMOS technology. Two different plasmonic materials, indium tin oxide and vanadium dioxide, have been characterized and used to design an electro absorption modulator. Both the modulators can be used in next generation photonic integrated circuits. Next point, a V-shaped ITO-based electro-absorption modulator is designed and investigated. With a change in structural parameters, a change in the performance matrices of the device was observed. The investigated modulator shows improved performance compared to contemporary ITO-based modulator in the literature.
Yeah. So third here, I forgot to tell that this third section here, it was published in Journal of Modern Optics. Am I right, Himanshu?
Yes,
This
Taylor and Francis.
yeah, Taylor and Frankis, this Journal of Modern Optics. It has also, do you know impact factor?
1.54.
1.554. Good. So yeah, please go ahead with organization of the thesis.
Okay, coming to section 1.8, organization of the thesis. The thesis consists of 6 chapters, and a brief description of each is as follows. An introduction to the silicon photonic market and a brief literature survey on silicon optical modulators have been presented in this chapter. Moreover, it contains motivation and objective problem formulation, scope of research, and the major contribution of the thesis and research contribution significance. The rest of the chapters are organized as follows. Chapter 2 presents various types of optical modulators, mathematical modeling of a directional coupler, and the performance matrices of a silicon optical modulator. This chapter will also discuss various types of methodologies used to carry out the performance matrices of an optical modulator. Chapter 3 discusses the design challenges and the solution for the architectural improvement of the optical modulator. Chapter 4 emphasizes on the behavioral characteristic of two different modulators based on vanadium dioxide and indium tin oxide. The material characteristics will be discussed and comparative analysis among contemporary devices will be done. Chapter 5 discusses the structural optimization of the device in terms of device dimensions, particularly the waveguide's height. A V-shaped electro-absorption modulator with different waveguide heights of 220 nanometer and 350 nanometer is designed and investigated. Also, a comparison of the investigated device along with a similar kind of devices will be presented in the chapter. Chapter 6 draws a conclusion from the contributions of the thesis. It presents the summary of the work done, limitation of the work, and the future scopes of this research work.
Yeah, so this is the just what are the content we are going to take up. So through in this way we have completed chapter one, very important chapter. So any question, Gitima, sorry.
Yes, sir.
Any question you would like to tell, or you want to reflect? Even you can reflect on how it was. What is your feeling out? Since
So it
we
was good.
yeah,
Yes, sir.
over to you.
Like Himanshu had said. Yes, sir. Sir, Himanshu he had selected two particular, I mean, plasmonic materials. You said there was like beyond the scope of this thesis. Like, what was the issues? Like other plasmonic materials he was unable to use or something. Hello.
Yeah, Himanshu. So can you tell beside you have used only two materials, so why you could not use that other plasmonic material? This is what Gitima is trying to ask. Is it correct, Gitima? Himanshu, can you hear
Yes,
me?
sir.
Yeah,
Yes,
please
sir, I
go
can
on.
hear you.
Yeah, please go ahead.
Okay. We have used only indium tin oxide and vanadium dioxide, but we have not gone for other like graphene and gallium dope zinc oxide. So we can use other plasmonic materials also, gallium and graphene. But the thing is that here we have used dielectric materials for ITO and VO2. Specifically for ITO, we have used hafnium dioxide. And for VO2, that is vanadium dioxide, we have used a dielectric material, silicon dioxide. So if we go for other materials like graphene and gallium dope zinc oxide, we have to go for aluminum dioxide and other materials.
Mhm.
So since going through two plasmonic material is itself a very, we can say, hectic process. So gallium dope zinc oxide and graphene, we have kept it for future scopes, since the calculations and materials we'll be using for gallium dope zinc oxide and graphene will be different.
Yeah, other dielectric materials has to be further characterized. So that is why, and with the limited time, he could not take up. But further researcher can take up this work. So that is good question and good scope. Means your work should further open the window to carry forward the work. So here the question is very pertinent. One can further develop this kind of modulator. Yes. Thank you, Gitima.
Thank you, sir. Thank you, Himanshu.
Anyone else want to reflect? See, this is a platform where opportunity has been given to speak out. We have to learn, okay, so that at bigger platform we can do better. So this is our, our smaller platform where we can have little bit practice, no problem. And don't afraid of committing mistake. Mistake is part of life, and one has to commit the mistake, then only one other is able to learn. So you might have thought that without falling on the bicycle no one will learn the bicycle. Okay, so this goes with this our research also. So don't hesitate to ask the questions. Okay, anything you want to from our side? This reading session is okay, or we should include some PPT, etc. I think reading is very important. PPT, though, every time we used to saw or hear, whenever even Himanshu is going to give his final defense at that time, also lot of PPT he will present. But PPT will suppress a lot of other information. But here, line by line, if we are reading, then we can understand in a better way. So we are trying to supplement what is left through the PPT. Okay, so already 1.5 hours you have given. Thank for showing your patience, being here, and making this program successful. We will take chapter 2 tomorrow, and same cooperation we will see. Okay, so please fill up this registration form so that we will have a list of participants. And at the end of this completion of our thesis reading, I will give a certificate to all. Is it okay?
Yes, sir.
Okay. So I will stop here recording.